Hello everybody, how are you all doing? Uh, this is the SAS review for test number 3. But before we do the review, we do have a quick announcement to make. And that is that we will have one in person, another review in person. So if you have any questions that you would like to have answered in person, you can still put them on Teams. So once again, I would suggest going on Teams if you have any questions. But we are also offering an additional review. So in addition to this, we will be having a review at 7 o'clock Thursday night in the engineering building in room 1107. We'll be going, I think, until 8:30. But yeah, we'll be there going over whatever questions you guys have. And if you don't have any questions, we'll be going over additional problems like this. So if you're able to make it, I do not think we'll be streaming this one. That's why we have this online recorded video still. But yes, if you can make it, and you have any questions that you feel need to be asked, come to this. Or if you can't make them, just put them on Teams, and we can go over them with you. And with that, let's go over the test. So real fast off the bat, there are some centrifugal force questions. I'm gonna skip over those for the most part, mainly because I do not believe those will be on the test. But if you do feel unconfident on the centrifugal force, I'll put a link in the video description to a independent video that explains the concept a bit clearer than I did last time. And now let's get on to the first question. So in this first one, they gave the component Fx of a force acting on a particle moving along the x-axis. And they want to know the amount of work done on the particle from 0 to x equals 1, from most positive to least positive. So remember, work is equal to, force times distance. So what we're really trying to do in this equation is get the area under the graph, and whichever area has the most under the graph will have the most positive work. Now, they don't exactly give you any values to work with here, but you can typically tell that this area here is more than this area, so we know that B is going to be greater than A. Also, judging by the rest of these, you can typically tell that B is going to have the largest positive area, so B is going to be the largest, followed then by A, because A seems to be evenly split between the positive and negative. So I have B, A, then C, I believe, because D has very little area above, and it's taken away by all this area beneath. So we have B, A, C, and then finally D. And then number 2 is a centrifugal force question. So this all should have been covered in the last test, so I don't believe you'll need to worry about a question like this. However, if you did get a question like this, if you do want to practice with it, the answers at the top will be going down. Normal force on the person. Oh, I'm sorry. So yeah, Since everything's in a circle, wow, that is one bad circle. But for this question, they want to have, since it's all in a circle, the acceleration, even if it's pointing in different directions, it'll always be inward. The acceleration for 1, 2, and 3 will always be equal. And then for the normal force, since the acceleration needs to be pointed inward, it'll be the greatest for the bottom, then the next for the middle part, and then the smallest for the top. And let's get on to number 3 now. So the block slides across the track through distance h. The track is frictionless until we reach this point here. They want to know what happens if we decrease the h. And the answer there is that the higher h is, the greater our potential energy will be. And thus, the greater the potential energy, the greater our total energy. So if we decrease h, we will have less energy here, so we'll be able to slide less far. So less than d. And so because we're going to get less potential energy here, we're going to have less energy at this point, which means it's going to be easier, or it's going to take a shorter time to pull the object completely to a stop. If we increase the mass, this one is a bit for energy. Once again, that's a bit with knowing the equations, because the potential energy is equal to mgh, and the kinetic energy is equal to mv squared over 2. And then the friction is equal to the normal force. The normal force is going to be equal to the mass times gravity times distance. So you can see here we have mass on each of these values. That means we can cross it all out, because even if we increase mass on one end here, it'll increase the same on all the other energies. So this one will be equal. So equal. Alright, and now on to problem 4. So we have an overhead for 4 particles. Yeah, so this one is, you likely had this all in the homework. So, but to reiterate, the first one, they want to know the center of mass. So you pretty much want your 2 particles to be keeping the same midpoint between them. So let's start with A and C. They have a point here. And then as they continue to go, C is going to move forward, A is going to move forward here. You can see that they're still going to have the same center, so A, C. In addition, we can say the same thing with CB, BC, and then also with CD. And in fact, and then BD does not work because they start here, then they go forward, their new place is right here. AB, start here, keep going. AD, they start here and they keep going. Alright, and so hopefully that makes sense. They want to know now with stationary and at the origin. So, we already determined which ones are stationary. Now we just need to figure out which ones are at the origin. Fortunately, there's only one of them. Since CD is here, AC is here, BC is the only one that is stationary and at the origin. So that's our answer there. And then they want to know passes through the origin. So that means that the object is, that the center of mass is moving. So we can already cross out these three. So that leaves us with BA, that never touches the origin, so we don't need to focus on it. DC, same thing. Oh wait, no, sorry, DC is covered here, that doesn't touch, even though it's stationary. We have BD, so we start here, and then as we keep going, our center of mass will eventually pass through here, since it's going in a straight line from here onward. So, BD does work. And then AD, well, we start here, although theoretically it will also follow the same horizontal x-axis. So AD is the other one. So BD and AD. And now let's move on to the last number 5, which was also covered in your homework, but pretty much the idea here that they're trying to cover is that your mass, your initial mass velocity is equal to your resultant mass 1v1 plus m2v2. So let's say that all the masses are 1 and your initial velocity is 1. We have 1 here. Let's also say that, so now let's figure out just the impact that changing the velocity for 2 has on velocity 1. So in this first one, they're both positive. Let's say that V1 is 0.5, or V2 is 0.5 here. That means this one's going to be 0.5, 1 times 0.5. And V1 will also have to be 0.5 in order to answer that. So, right here, V1 is going to have to be 0.5 to satisfy. And if you plugged in like different, and this is just an example, but if you plug in other numbers, this will still turn out to be correct. You'll still get the same end result if you're doing with positive, negative, and 0. So now with C we have V2 is equal to 0. So 1 is equal to 1. Our V1 is going to be equal to 1. So already we have C is greater than A. Then finally B, let's say it's negative. 1 is equal to negative 0.5. And that means this one has to be 1.5. So we have 1.5 and 1 and 0.5. So we have B, C, A. Alright, so now let's go on to longer questions. This first one is center of mass. Fortunately, they broke it up very nicely. I believe that if you have a center of mass on the test, it will be kind of like this, only instead they'll probably have like a third mass that's attached right here or something. But that's not what we have on this problem. if you do have a third mass, you treat it just the same as the others, because you just combine it with the rest and calculate the equations the same. So for the first one, they want you to find the center of mass for the left rectangle. For this one, they give us L, so we know that it's going to be up at the middle here. So we can say that this first one is going to be negative 1L to the left, which is negative 5, and 1.5 up, so 7.5 in the y direction. And if they wanted mass, I would say typically assume each 1 centimeter square is 1 kilogram. So we have 15 times 10, that's 150 kilograms. And now they want you to do the same thing for this one. So let's do the x-axis first. That is 2 times 10. It's in the middle once again. That is 10. Also make sure to put these in centimeters. So both these are in centimeters. Now for the y. So this is in the middle, so it will be 0.5 from this point. However, first we need to take it up to L to get to the bottom layer. So this should be 2.5 L high, because we have 2 coming up here, L, and then we have another 0.5 taking us the rest of the way. And that should get us to our value of 12.5 and centimeters. Now what they want us to do, and then also I'm going to write the mass, so we have 5 times 20, which is around 100 kilograms. If you want to do a different mass, that is fine. All the masses, no matter which one you choose, they should still get you the same center of mass at the end, as long as you're consistent. So now they want us to combine, so let's do x first. How this works is you want to just do x1 times m1 over m1 plus m2, and then you have plus x2 times m2. And then if you hypothetically had a third mass, so this is not related to this problem, but if you did have a third area, you would do x3 times m3 and then plus m3 on the bottom. So hopefully that made sense. I'll just keep going now with this. So we plug in our values. We have negative 5 times 150 and 10 times 100. So that should get us equal. Multiply this out. That's 750, 1,000. That's 250 over, this is centimeters times kilograms, over 250 kilograms. which gives us our final value of 1 centimeter. Now for our next one, that's our x. For y, it's the same thing. y1, m1, plus y2, m2, over the total mass. Since we already calculated the total mass, it's going to be 250 as well. And now we just plug in our values. We have 12.5 and 7.5. So if you plug in those values, you should get your value on the top of 230 over 250 This will be in centimeters. And that gives us a final value, y of 9.5 centimeters. And this is our y. This is our x. And hopefully that made sense how to do it. Also, if they don't want mass, you can also replace these masses with area. So mass is approximately area. So if you don't feel comfortable doing mass, just do the area of each of these instead. That should get you the same result. This is the centrifugal force one. It's not that, you shouldn't have to deal with anything here. It's something, they should have had this on the previous test, so I cannot see them putting one of these on this test, so I'll keep going. If you do want me to go over this, just put it in Teams or bring it up at the review session Thursday at 7. Alright, in this one, so right here we're going to start with potential energy. We have a ball, mass, so this is basically, they want to know how fast the ball is going when it's swung down from here and hits this block. So this is pretty much just a simple, we start with potential energy, and by the end that's all going to be converted to, to kinetic energy. So our potential energy, we can say that the height is also the radius of the ball. So if we follow this distance, that's the height. So the rate, which is equal to the r. So we just do our m. So PE is mgh. So we have is equal to 0.3 times 0.7 times the radius. No, I'm sorry. That was backwards. This should be the 9.8 for gravity times 0.7. And that should get us our value of 0.21 multiplied by 9.8, which is roughly 2.06. joules. And after that, we just want to set this equal to our kinetic energy. So this is our potential energy. We set it equal to our kinetic energy. Our kinetic energy is mv squared over 2. So we just plug in our values for that. And we get that. This is mass just for the ball, because the block hasn't come into play yet. So we substitute our values there. We're going to get v squared is equal to 13.72. We take the square root. And we get our answer of 3.7 meters per second. So hopefully that makes sense. It's just converted from potential energy to kinetic energy. You set these two equations equal to each other, and you use that to find the missing variable. So now they want to know the speed of the ball on the block. The ball and the block stick together. So how this basically works is, if you recall what we were doing here, that's basically what we'll be doing now. So we have our initial mass, which is the mass of the ball, mass 1, times v1, or ball right before it strikes. And since it's going, so our initial values, plus 0, since the block was not moving before, are equal to our combined forces after. So the m1 plus m2 multiplied by our new v value, and what we want to do now is just plug in these values. So we have 0.3 times 3.7, and then we want to divide, so that gives us 1.11 is equal to 1.3 if we combine the masses times v. So divide that by 1.3, and we get our answer of our new speed is 0.85 meters per second. And that's our answer there. So we will be doing C now. During this collision, how much energy is converted to heat and sound? Alright, so that's good. So basically how that works is we have, since we have our kinetic energy here, we want to know how much energy is lost. So we have our initial kinetic energy before it strikes. And remember, energy has to stay consistent. If it doesn't, all the energy that goes out, it all goes out into heat. So our initial kinetic energy, this initial, plus our energy from heat, which is what we're trying to find. So our initial kinetic energy, we already know that. That would be the 2.06. We could also get that from doing our mass times velocity squared. since we know velocity, but this just makes it slightly easier. And then we set that equal to EF, which is our ending velocity times mass. That would be, so our mass is 1.3 times point times 0.85 squared over 2 plus EH. So we just multiply these values out. This should get us our answer of, well, our point. This here equals 0.47 plus EH. We subtract the 0.47 over, and we're going to get 1.59 equals EH. Equals EH. And that's our answer here. So that's how much energy we lose. We can then determine that so what we then want to do is determine, so hopefully that answer made sense. Now we want to determine the maximum height above the surface that the ball will rise. So this is just going back and converting kinetic energy into potential. Our new kinetic energy is our value of, is on one that we calculated right here. So we have 0.47 is equal to PE, which is mgh. And remember, our mass is now 1.3. So we have 1.3, 9.8 times height. And then we just divide everything out. We get 0.47 divided by 9.8, then divided again by 1.3, and we have H is equal to 0.037 meters. And that should be our answer. Yep, they rounded slightly different, but we had, yep, that is the correct answer. Right now, so for this next problem, they put the equation at the bottom. Always make sure you have that next to you. So what we want to do for problem number 9 is they have a block of mass 2.5 slides into a spring, K constant. They want you to know the work done by the spring force. So, pretty much what you want to be doing now is, I'll use this as an example to see if they have the spring force. Yep, so it's right here. The work done by the spring is equal to 1/2 kx squared. So if you ever don't feel like you know what to do, just try going down to the equation sheet. That will likely help give you at least an equation to use. So, the work done by the spring is equal to 1/2 times k, then multiplied by the distance traveled x. And that gives us, so that we want to then simplify this out, we know that this is 320 divided by 2, that's 160. This is also squared. Newton by 0.75. I believe, yeah. What we want to do, since this is in centimeters, you also see that this K is in meters. We want to convert this to meters as well. So this will actually be 0.075 squared. And that will get us a total work of 0.9 joules. So that is the total work done by the spring force. We got the distance by how much it compresses. Yep. And then they want to know the increase of thermal energy on the block floor system. So the increase is just basically the friction. So they want to know the friction force. And work is always equal to force times distance. So we want to multiply our force of friction. So F friction. We want to multiply our force of friction by the distance, which is how far it travels. So force of friction is 2.5. So the normal force multiplied by the mass multiplied by gravity to give us the normal force. Then we multiply that by the coefficient of friction. And that will give us our eventual value. Of 6.125. We then multiply that force by the distance. So 6.125 multiplied by 0.075, which gives us 0.46 joules. what they then want to know is the block's speed just as it reaches the spring. So that's pretty easy. Once again, we need to remember that the total energy, stays constant. So if right here to here, the block loses 0.9 joules to the spring and 0.46 to the friction, that means that the total energy when the block hits the spring has to be equal to these two combined. So we do 1.36 joules, because that's how much these two are summed. And then right here, we can assume that there's no potential energy, there's no height. So we can assume that kinetic energy at this point is also equal to 1.36 joules. And then we just set that equal to our kinetic energy equation. So we have 1/2 mv squared. Plug in our values, we get v squared is equal to 1.088. And then we just take the square root to produce our final answer. V is equal to, I think that's roughly like 0.4. Yeah, 1.0 1.043 meters per second. This is meters squared over seconds squared. And that's our final answer. And that's pretty much all we have for this test. If we go over some problems Thursday, I'll try to record those as well. But once again, if you have any questions, please come by Thursday at 7 to engineering room 1107. We'll be there until 8:30. And then, or post it in Teams. Post it in Teams. We have this test, and then a second test by Bolton there as well. So if you want any extra practice, feel free to go on Teams and check out those two quizzes. Anyway, thank you, and we hope you have a wonderful day. Hopefully we'll see you Thursday.